Hello, everybody. Thanks for joining. We'll begin quickly.
Hi, everyone. Good morning. I think we can wait for one more minute for other participants to join. Hi, everyone. I'm Mu'taz Dakouri, your host for today. Thank you very much for joining. I think we are good to start. We have 39 participants. So, hi everyone. My name is Mu'taz Dakouri. I'm a research associate and refrigeration expert at the International Institute of Refrigeration. I have with me today my associates Kavya and Anna, who will be supporting us in the backstage. And on behalf of the IAR and our co-organizers, the Association of Heat Pump, the European Heat Pump Association, and the IEECP, we would like to welcome you today to this webinar. So today's workshop is about the dairy sector's energy transition in practice, not in theory. And in the following 90 minutes, we will focus on featuring real numbers, real supply chain analyzed end to end, and 3 practical tools you can use in your own company. So let's get started. So let's start with the important question as why does this matter? Why now? And actually, Europe's dairy sector still covers from 60 to 80% of its energy needs with fossil fuels. And the business case for change is already proven. Industrial heat pump projects are delivering 36 to 59% CO2 reductions in operating dairy plants. And for instance, a French milk and cheese manufacturer is saving 125,000 euros per year after replacing its gas steam boilers with heat recovery chillers and high temperature heat pumps. The technology works, the savings are real, but what's missing, especially for SMEs, is the technical capacity and clear investment case. That is exactly the gap our project BETTED closes. BETTED, which stands for Boosting Energy Transition for the Dairy Value Chain is a 3-year initiative co-funded by the EU LIFE program and led by the University of Prishka. The project is dedicated to promoting energy efficiency and the adoption of renewable energy in the dairy sector. By promoting the integration of renewable energy and heat pumps, it aims to reduce dependence on fossil fuels and accelerate the energy transition throughout the dairy value chain. In this context, BETTED develops a free training program on selected topics backed by a suite of efficiency heat pumps, biogas, is dedicated to staff across the value chain of industries with some topics specified to the dairy chain. And this is equally open to companies providing technologies, equipment, supplies, or maintenance services, as well as funding bodies and policymakers dealing with the industrial sector. Everything is free and everything is funded by the EU LIFE program. And in this context, this workshop is part of a series of workshops that is provided by the consortium members, and IAR is glad to host the second workshop in the series. The session is being recorded and your microphones are muted, so please post questions in the chat or Q&A box at any time. We will address them at the end, and at 11:50, I will show you exactly how your company can apply for a free full-day training session as part of the project. So let's get started. So I'm delighted to hand over to Beatrice Markey from the University of Prishka, which is the lead partner of BETTED, who will present the BETTED toolbox consisting of 7 free tools covering the dairy value chain, and then show them at work in a real supply chain. So, Patricia, the floor is yours.
Okay, thank you for the introduction. So I will share the screen. Okay, can you confirm that you see my presentation?
Yes, we can see it.
Okay, thank you. So I'm Beatrice Marchi. I work at the University of Brescia, and as you said, we coordinated this project, which aim is, as you already said, to support the energy transition for the dairy supply chain. So one of the main objectives of the project was to support not only individual companies, but the overall supply chain, value chain, in order to reach the optimal performance from a systemic point of view. This is very relevant in general, but also for this specific sector, because the collaboration among the different stages of the supply chain can support the achievement of improved performance, because there are new opportunities that a blinded individual perspective cannot have, and also because the collaboration can support also the overcoming of the existing barrier. Among the project is mainly built upon 3 different pillars. The first one is to build a capacity building program, and also a shared community in order to allow the different actors of the value chain to share knowledge and information on the energy transition, so on technologies, on systems, and on lesson learned from previous project and also in this project. The second pillar is the development of a toolbox that I will show you in this presentation. The aim of the toolbox is not to provide too detailed analysis that are relevant only for expert personnel, but the idea was to allow also non-energy experts, which are mainly operator of that specific value chain, in order to support them in first assessment of the supply chain energy consumption and also on the evaluation of the main technologies and the main energy efficiency measures. The third pillar is mainly focused on policy. So in this project, we had a focus also on supporting the European Commission on the different policy that can support this energy transition. So we interviewed many companies from the dairy sector, trying to understand which are the main barriers right now, and so trying to translate this information that we had from the field in order to support the development of policies that can support the energy transition. So this today I will focus on the toolbox. The toolbox is available online, so it is free. There are 7 different tools that can be downloaded, so everyone can use these different tools on offline, so you don't need a connection, you don't need to share any data. And they are in English, but of course we can support also everyone in the translation and in the use of the different tools. As I said, there are 7 different tools that try to cover the energy transition from different perspectives. The first tool is the dairy supply chain tool, which try to answer to the question on that companies might have to understand the energy consumption, so to try to map the energy flow, not only from the individual point of view, but of course considering all the value chain. So the aim is to have a first assessment on which are the main energy carrier, which are the main hotspots along the supply chain, which are the main measures that we can consider in order to reduce the overall energy consumption. So each one of the tools mainly consists in one input sheet where some data are required, and then the results are presented. For this specific tool, the input mainly are requested for each one of the transportation stage and each one of the storage and production stages. So since the focus is on the supply chain, we developed we consider in this tool 7 different stages. So we start from the raw material supplier, the transportation of raw material supplier to the production process, the production process stage, then the transportation to the distribution center, if any, the distribution center itself, and then the last stages are the retailers, so where the final customer access to the final product, and the transportation from the distribution center to the retailer. The tool is based on these 7 stages, but of course it is not necessary to consider all of them. So even in the case study that I will present, it is possible to observe that some of the stages can be covered by the same company, and some stages can be also neglected because maybe they are not relevant for the specific case study. An important note on this tool is that it is not necessary to obtain data from each one of the supplier, each one of the distribution center, each one of the retailers. But the main idea is that only the strategic one or the most relevant one should be included. So the data that are required are mainly focused on the energy requirement, so energy consumption, and also on some operational data. For example, if we consider transport, also how many trips, the average distance between the different stages, in order to support also the user in investigating more in detail this data and the information that the tool can provide. As a result, we can obtain a map of the energy consumption. In particular, the indicator is the specific energy consumption, so the overall energy consumption divided by the output that the value chain provide to the final customer. And also we have information on the specific stages, as you can see from the graph, and also on the energy carrier. So different color means different energy carrier, and each one of the bar represent a specific stage of the supply chain. In this way, it is possible to understand which are the main hotspots. In this case, are the illustrative example are the producer and the distribution center, and also the energy carrier is the electricity. So based on this first analysis, it is possible to try to think about which one of the best practices of the energy efficiency measure can be considered in order to reduce the overall consumption. The second tool is aligned with this first tool, but it shifts the focus on a life cycle assessment tool. So it is not only focused on the energy consumption, but it includes the environmental impact perspective. So the structure and the result are similar, but are in this case are requested some more information about other inventory data that can provide an impact on the environmental perspective. And the three indicators that we consider in the result are the global warming potential, so the CO2 equivalent per kilogram of final product, the cumulated energy demand, so megajoule per kilograms, and the water use. So we consider these three indicators because these are the most relevant for the dairy value chain, and the idea was to also have a simplified life cycle assessment. So life cycle assessment is comprehensive, detailed, but it is also complex to use. And so with this easy to use tool, the idea is that also non-expert and companies or users that have few data, access to few data, can have this first assessment. So the result, the idea, this tool provides some result that complete the analysis that the first tool provide. So in this case, we have a wider perspective, also considering other relevant environmental impact. Based on the first and on the second tool, and based on the material that is available from the website that consists of a list or some best practices on energy efficiency measure, it is possible to start to have a first list of energy efficiency measure with potential for our specific value chain. The next step is tool number 3, that is focused on one different energy efficiency measure that we select with the support of the first and the second tool. And the idea is now to investigate if these measures are feasible from the economic point of view. So the life cycle costing tool, also in this case, is a simplified tool in order to have this first assessment. The aim is to understand cost and benefit of different energy efficiency measures and to compare their behavior to the current state, so the scenario without any energy efficiency measure. The life cycle cost include an input data that a template that supports the user in order to ask himself which are the main costs and benefit that we can observe with the specific measure. So the result of this tool are tailored to the value chain, but also to the measure that we are considering. As a result, we have some indicators that some economic performance indicators like the net present value, the internal rate of return, and the profit index. With this result, we can prioritize the energy efficiency measure that we select based on the analysis that we perform with the previous tool, and to prioritize them with an economic point of view. These tools are focused on the supply chain, and in the first assessment of this energy efficiency measure, now we have some tools that are focused on specific measures. So we start with the biogas in the dairy chain. This tool is a bit more complex compared with the previous one, and asks some input data to the user, and in output provide a first techno and economic assessment on the use of biogas in the specific dairy chain that we are considering. The data required are a bit more complex and detailed, but there are also default data that can support the user if the user has not access to all this information. So also in that case, the idea is to have the first assessment. So the idea is not to design the biogas and the plant. The idea is to start thinking about this potential opportunity and to think if it makes sense to go on with the design of it. Tool number 5 is focused on heat pumps. So in this case, there are very few data required as input data, and the idea is not to design heat pumps, but is to show the user how the performance change in terms of say economic savings and on emissions reduction by changing the coefficient of performance of the heat pumps, and also by changing the share of renewables that covers the electricity demand for the use of these heat pumps. So this is a first assessment. Of course, changing the coefficient of performance changes the performance, but these tools support this first assessment in order to also see the heat pumps make sense if the coefficient of performance is between a range of specific values for the coefficient of performance. The last two tools are no more focused on technologies, but are focused on the tool number 6 on the cooperation with different actors. So the idea is that the strongest companies inside the value chain can support the partners in order to improve their environmental and energy performance. So tool number 6 is a questionnaire that support the evaluation, the assessment on how the different partners, the different actors of the value chain behave in terms of sustainability. So there are 5 different sections covering climate impact, biodiversity and conservation, sustainability transition, social responsibility and governance, and energy efficiency, with several questions. And based on the answer that each actor, each company provide, it is possible to evaluate, to assess a score, to provide a score for each one of the actors. In this way, it is possible to assess which are the weakest companies, which are the main issues, and so also to provide, not to score them, but the idea is that based on this result, it is possible to provide some input and support their improvement. The last tool is the non-energy benefit evaluator. So usually when we consider the economic feasibility, we consider the energy savings deriving from the implementation of a specific measure. But this is not all the benefit that the measure can introduce. So the non-energy benefit evaluator is a tool that supports the assessment of all the possible benefit that a specific measure can provide to a specific supply chain. So in that case, it is not only a list of potential benefit, but the tool support the user to investigate also which can be the what can be the impact of this specific benefit. So it can improve the value proposition, can reduce cost, or will impact on the risk. So based on this template, it is possible to identify all the relevant non-energy benefit, understand which is their strategic impact. So in order to make also more strategic the measure to the financial officers, so to the actor inside the company that should say yes to the specific investment, and also can support the user in defining how to monitor this specific benefit. So I have shown very briefly the tools. There is a channel on YouTube that provide more detailed videos for each one of the tools. So if you want, you can go to the YouTube channel and see more in detail also how to fill in the template, which input data required, with some example. Now we move to a best practice. So we use the tool number 1 in order to assess the energy performance of a dairy chain in Italy, which produce grana padano. So a seasoned cheese with some specific requirement from the dairy production. So it is there are strict regulations that govern this specific production process. Operational context, the dairy chain that we consider start from raw material as milk raw, and the milk is then supplied to the production process, which can produce, as I said, seasoned cheese, grana padano, with about 8 to 10 liters of milk for 1 kilo of cheese. During the production process, also whey is produced, about 6 to 7 liters per kilo of final product. And the infrastructure, we start this analysis starting from the producer. So we had the producer is the strongest company of this specific value chain, and so we started with them, and thanks to their support we reached also their supplier and the transportation activities, and also the retailers. They have also an internal warehouses, quite big internal warehouse, and we start. This is the scope of the analysis. So dairy processing is our core company, which process the milk, make the cheese, cooking, ripening from 9 to 24 months. But the scope is not focused only on that stages. We included also suppliers, so starting from milk collection and on-farm cooling, transportation from the supplier to the dairy processing with a refrigerated tanker, and then the final step is the distribution and retail. In this specific case, we also included the transportation from the processing to the retail, but it is quite negligible because they have their store near their production plant. And so we also included the data, but of course the result will be negligible. So the focus of this analysis was the entire life cycle from milk to grana padano cheese in a local dairy supply chain. We start with the energy consumption analysis. So with the use of tool number 1, we inserted all the data that are required, aggregated data on an yearly basis. And we can observe that the production stage is the largest energy consumer, and exceed the contribution also of the other partners. Another interesting aspect is the energy carrier. So the producer is mainly consuming electricity, and relevant but not as electricity share of natural gas. Natural gas is less relevant than electricity in share, but it presents the higher potential in terms of energy transition, so in electrification of the value chain. Transportation is relevant also transportation, and the main energy carrier is gas oil, and so also in that case there can be some interesting measure that can support the energy transition. So with the information that we had from the companies, we also investigate how energy is consumed among the different stages. So for on-farm milk cooling, there is, and also in transportation, there is the cold chain challenge. So milk should be refrigerated and kept at 4 degrees Celsius. And so even if they are not so relevant as in the production stages, they are very relevant because this refrigeration is needed to guarantee the quality of milk and so to avoid waste along the supply chain. And transportation in that specific case was not so relevant because we consider a local dairy chain. So the average round trip distance was not so big, so 30 kilometers. And so the power that we need to cool the milk between the supplier to the producer should work only for a few limited amount of time. We then focus on the producer, starting from the electricity hotspot. So we try to investigate where are we consuming electricity, and we observed that the main electricity consumption was in the cheese ripening. So we are no more speaking about milk, we are speaking about cheese that should be ripened, so seasoned cheese. So the temperature requirements are no more stringent like for milk. We are no more speaking about 4 degrees Celsius, but we need refrigeration, even if it is low. There is lower power of refrigeration, so a lower load of refrigeration of cooling demand. We need this lower cooling demand for a longer period. So the warehouse, the ripening warehouse is working all day, all week, all the year. So even if the demand in terms of power is very low compared to the milk storage, we need this cool for a lot all the year. And yes, not only for temperature, but also for relative humidity and ventilation. So in order to guarantee the quality of the final product, there are stringent requirements in terms of temperature, but also humidity and also ventilation. And so our main hotspot for electricity consumption is based on the guaranteeing this requirement of the condition where we store the cheese. For the thermal hotspot, so we observed previously from the bar of the producer that natural gas is less relevant than electricity, but it is a huge consumption if we think about its environmental impact. And so we also in that case go deeper trying to understand where we are consuming natural gas, and we observed that 20% was for space heating, 30% was for hot water production, while half of the consumption of natural gas was for the process. And so these provide us the information that this 50% of natural gas that is consumed for the process represent a relevant opportunity for the decarbonization, for example, with the electrification using heat pumps. The last stage was the retail distribution, so the transportation was made internally, so it is not so relevant. The final stage, also in this case, it is not relevant as the other stages, so transportation and producer, but there are a lot of inefficiencies because most of the energy consumption are related to at least half of the energy consumption are related to the refrigeration of the display cabinets and the cold rooms, which are subject to a huge number of door openings, and if they are not sealed well, they can provide a lot of wasted cooling. And so this is not our focus, but of course there is a lot to do also in this specific stage. So based on the assessment of the opportunities for each one of these stages, we provided 3 to-be roadmaps, so 3 different scenarios in order to improve the performance of the value chain. The scenario number 1 was the a scenario where we suggested the producer to implement a photovoltaic system on their warehouse. So this is not an energy efficiency measure, but of course this is a relevant measure if we are talking about transition, so the decarbonization of our dairy value chain, because we can provide electricity with green energy instead of fossil fuel. Scenario number 2 was focused on the improvement of efficiency of refrigeration equipment, while scenario number 3 was focused on the heat electrification with the use of heat pumps. So these 3 scenarios were based mainly on the overall object to decarbonize the dairy value chain, so to support the energy transition of our case study. So as I said, in scenario number 1, we investigate the installation of a PV system supported with battery energy system storage. And the idea is that we can cover the electricity demand with our PV system, and the battery allow us also to cover the demand during the night periods, because as we said, our main consumption of electricity was in the warehouse, and the warehouse should keep the same condition also during night. And so our consumption is not linked to the daily process, but are relevant also during night. And so the idea to integrate the battery storage is to cover also this night consumption. We consider also the installation of some sensor and some variable speed ventilation system in order to modulate the energy in order to the required condition that the warehouse has. Based on the assumption that we consider a PV system that cover about the 30% of the annual electricity demand, using the tools that we presented before, we analyze the 2B scenario, and the expected outcome is that we can obtain a significant reduction in indirect emission, because of course we are no more using fossil fuels but green energy. Second scenario is improved equipment for refrigeration. So we included the heat recovery from the refrigeration unit and improved thermal insulation. This scenario allows us to reduce the auxiliary cooling capacity by 20-40% and also allow us to reduce the peak electricity. Scenario number 3 was the transition to heat pumps. Heat pumps increases the demand for electricity, but allow us to reduce by half of the 50% the consumption of natural gas. So comparing the overall performance, the increase of electricity justified this reduction. Well, the reduction of the natural gas consumption justified this little increase in the electricity consumption, especially if we implemented the PV system. So considering all the measures, we observe that comparing the current state to the scenario where all the measures were implemented, we reduced by 11% the specific energy consumption, by 24% the total annual cost, and by 26% the overall emission per year. The key takeaways from this case study is that not all the dairy value chain, the dairy value chain, since we are talking about food, are subject to stringent regulation of the ambient, the condition where we store and the product, raw material and final product. But there is a huge potential in order to improve the overall performance while keeping the quality of the product. So we are not talking, we reduce consumption, but a quality cost. It is possible to improve the overall performance while keeping the quality of our product. So, and in this specific case study, we identified this pre-scenario, but there are, of course, a lot of other opportunities. So thank you. If you have any question, of course, I will be glad to answer.
Thank you very much, Beatrice, for the comprehensive overview of the toolbox and outlining different technologies that are used in boosting energy transition in the dairy value chain. So I think that before choosing any single technology, stakeholders need to know where the sector stands and what the EU regulatory framework requires and which efficiency measures are on the table. So to give us exactly that, I hand over to Giulia Baldelli from the Institute for European Energy and Carbon Policy. Over to you, Giulia.
Thank you, Matthias. So I just shared the screen. Okay, you should be able to see it now. Thank you very much. Good morning, everyone. So during this presentation, I will first provide an overview of the current energy outlook and EU policy framework, and then discuss the energy efficiency measures that can be adopted in the dairy sector. Okay, so this is the table of contents that we will follow. And okay, so at EU level, there's a number of policies and regulations aiming at increasing the share of renewable energy sources to improve energy efficiency and to reduce the greenhouse gas emissions. Starting with the Green Deal and the EU climate law. So the Green Deal aims to cut emissions by at least 55% by 2030. And it has also a very ambitious goal of reaching the climate neutrality by 2050. The renovation wave instead focuses on the building sector. So 85% of the EU building stock was built before 2001, and only 11% of this stock undergoes some level of renovation each year. And very rarely the renovation works address the energy performance of buildings. So the renovation wave aims to renovate 35 million of buildings by 2030 and reducing by 60% the greenhouse gas emissions, by 14% the final energy consumption, and to increase the renovation rate to 2% by 2030. So the renovation wave is closely linked to the Energy Performance of Building Directive, the EPBD. So around 40% of the energy consumed in the EU is used in buildings, and the EPBD aims to reduce, to achieve a fully decarbonized building stock by 2050. Covering 4 different areas. The renovation, so each EU member state will develop its own national building renovation plan. For non-residential building, the PBD introduces minimum energy performance standards, while for the residential buildings, each EU country will adopt its own trajectory to reduce the average primary energy consumption by 16% by 2030. There are also other areas covered by the PBD that are the decarbonization, modernization and digitalization, and financing and technical assistance. Then we have the RED II, so the Renewable Energy Directive that promotes the use of renewable energy sources. And the main objective is to increase the share of renewable energies in the EU energy mix and to support the transition towards climate neutrality by 2050. So the directive established a target for renewable energy consumption of at least 32% of the EU final energy consumption by 2030, And this target has been also increased to 42.5% of renewable energy and final energy consumption, still by 2030 with the RED 3, so the new one. Then we have the EU emission trading system, so the ETS, that is basically the carbon market where polluters need to pay for their greenhouse gas emissions. It covers emissions from electricity and heat generated industrial, manufacturing, aviation, and maritime sector, maritime transport. And it's based on the cap and trade principle. And together with the ETS, there's also the effort sharing regulation. So the ESR establishes for each member state a national target for reducing greenhouse gas emissions by 2030. And it covers those sectors not covered by the ETS, so domestic transport, not aviation, building, agriculture, small industry, and waste. And emission cover account for 66% of the EU total domestic emissions. Then we have the Energy Efficiency Directive, but I will talk about this in the next slide. And we have taxonomy and governance regulations where the member states are required to develop a 10-year integrated national energy and climate plans, highlighting how they will achieve the goals on energy and climate, and the long-term renovation strategy to support the renovation of the national stock of both residential and non-residential buildings, both private and public. So energy efficiency has been tackled by several directives. The most important is the Energy Efficiency Directive, the revised EED that sets a binding target to reduce both the primary and the final energy consumption by 11.7% at least by 2030 compared to the 2020 EU reference scenarios. It also extends existing energy saving obligations, and it aims at empowering consumers by granting them the access to the data on their consumptions. And finally, it introduces an annual energy consumption reduction target of 1.9% for the public sector. The energy performance of buildings cover a wide range of policies and supporting measures for improving energy efficiency of buildings. There's a clear vision for the complete decarbonization of the building stock by 2050, also thanks to the introduction of smart and efficient buildings through the use of ICT and the smart technologies. The industrial sector is well covered by Article 11 of the Energy Efficiency Directive. So since the recast of the EED, this article shifted from a size-based logic to a consumption-based logic, meaning that regardless the size of a company, those companies with an annual energy consumption above 10 terajoule, that is the threshold, will need to undergo an energy audit. For those companies with an annual energy consumption above 85 terajoule will need to undertake an energy management systems, regardless the size of the company. And then also the EU taxonomy and the EU directive on corporate sustainability cover the industry sector. Focusing instead on the EU dairy sector, this is the second biggest agricultural sector in the EU, and it accounts for 12%, more than 12% of the total agricultural output. The data come from Eurostat database year 2022, where EU was leading globally with 160 million tons of milk produced, and more than 94% of this milk was delivered to dairy facilities for the production of dairy products such as cheese, butter, yogurt. So there were around 12,000 processing facilities throughout Europe, collaborating with more than 650,000 dairy farmers. The European agricultural sector operates under strict food safety, animal welfare regulations, and the common agricultural policy provides financial support to farmers. The future growth opportunities are driven by the global demand, but the sector must also address price volatility, climate change, and sustainability challenges. This is a picture of the production of milk in the EU in year 2022. So most of the milk produced comes from cows, and basically 94% of the milk is delivered to dairies for the processing, and 33% of this is used to produce fresh products. Mainly drinking milk, and then manufactured products such as cheese, milk powder, butter, and a big percentage is converted into whey. So the industry sector is the largest energy consumer in the EU and is responsible for around a third of the total energy consumption. The food sector ranks as the fifth, so fifth largest energy consumers and greenhouse gas emitter, just following the energy-intensive industries. Also, the consumption due to the heating processes required in the dairy sector is increasing, and it also accounts for 62% of the greenhouse gas emissions in this sector. According to the IEA report of 2020, so 59% of total industrial energy saving in EU could be achieved in less energy-intensive sectors, meaning that before the recast of the EUD, only large companies were obliged to undergo energy audits and energy management systems. So SMEs were excluded by this article, from this article, and in the dairy sector, more, and as in many other manufacturing sector, more than 99% of companies are actually SMEs. So that's where this study comes from. So the environmental impact, the food industry, global emissions account for 15%. And emission from food waste account for 24%. These are mainly due to food waste along the supply chain that accounts for 15%, and also emission from food waste at the end consumers that account for 9%. So there are, of course, some relevant negative consequences of this food waste. First of all, the production of greenhouse gases emissions, the societal impact of wasting food in a world where the demand is always growing and it's unevenly distributed, the exploitation of resources such as land and water, and the loss of energy consumed for the processing and storing of the food along the supply chain. So the food sector accounts for around 17% of the EU gross energy consumption, and the industrial processing, including the dairy ones, represent 28% of the energy used within the food sector. There are energy-intensive processes that require heat, such as pasteurization and drying, and also the refrigeration. And these contribute heavily to the energy consumption and often heavily rely on fossil fuel. This highlights the need for energy efficiency and introduction of renewable energy sources. Adoption of renewable energy can be, for example, biogas from dairy waste, from manure, and from organic residues that can reduce the consumption of fossil fuel, turning this waste into renewable energy. heat pumps that can reduce the energy consumption by up to 40% compared to the traditional heating systems, using heat extracted from ambient air or from the ground heat to provide both space heating and hot water for operations in the farm. And the solar photovoltaic systems to generate and use the electricity on site, reducing the reliance on the grid, and also lowering the carbon footprint of dairy operations. Here is some energy efficiency measures that can be adopted in the dairy sector in different steps of the value chain. First of all, the introduction of energy management system and energy auditing to better understand the area where energy is mostly consumed, or whether there is waste of energy in some processes. Then the introduction of pre-coolers and heat recovery systems. So in order to transfer the heat from the raw milk to an intermediary cooling fluid before it's cooled down. The heat recovery system that can capture waste heat from milk cooling, but also from refrigeration processes to heat up water used for cleaning or for other operations in the farm. Install efficient lighting, so install LED lighting and motion sensors in the facilities. LED lights consume up to 70% less energy than traditional bulbs, and they also have a longer lifespan, and so they reduce the maintenance costs. Properly insulating the steam pipes to reduce heat losses and lowering the fuel consumption for heating. Also, optimization of the compressed air system, so regular maintenance to detect whether there are leakages and reduce the energy wasted. Also considered variable speed air compressor for increased efficiency. And finally, efficient HVAC system, so install heating, ventilation and air conditioning systems able to optimize temperature and ventilations. And to allow zone heating, so this allows to have targeted heating depending on the different zone of the facility, reducing the energy needed to maintain comfortable temperatures across all the facility. And that was all. Thank you. Before handing back to Matthias, I would like to mention that we will share a link to access a survey because we would like to hear a feedback from you on this workshop. So we will share it in the chat and also later after the workshop. Thank you.
Thank you very much, Julia, for the big picture overview of the EU regulatory framework, and for mentioning the different measures that can be implemented. Actually, after hearing that heating is responsible for the majority of the sector's emissions, and that heat pumps can reduce energy consumption by up to 40%, I think that we are all interested to know how this technology, the heat pumps, actually look like at an industrial scale and who is already running it. And for this, we have Paola Maio from the European Heat Pump Association, who will show us with real case studies from the food and beverage sector. So Paola, over to you. Julia, can you please?
Yes.
Oh, yeah. Paola, we can't hear you.
Yes, thank you. Can you hear me and you see my presentation?
Yeah, loud and clear. We can see your screen, but we can see it in the presenter mode. So I think you will need to present it. So hit F5 or press present. Yes, we can now see it. Oops.
You can see it now.
Yeah, we can see it now. Thank you. Please go ahead.
Thank you so much. Okay, so hello everyone. I'm Paola Maio from the European Heat Pump Association, and today I will give you an overview of the industrial heat pump technology and their potential to support industrial decarbonization. As also heat pump is one of the topics that we developed in the BETTED project. We will explore how mature the technology is, where it is already been successfully implemented, and what needs to happen to overcome current barriers and unlock a wider market uptake. Just a few words about EHPA, the European Heat Pump Association. We were founded on the 2000. We have around 200 members, and we represent the whole value chain of heat pumps. So our members are not only the heat pump component manufacturers, but it goes a bit broader. We also have a national heat pump association, test lab, utilities, and consultancies as members. And our main vision is to reach a fully decarbonized Europe where mainly heat pump technology are used. Here you can see that heat pumps are currently a mature technology and they are used everywhere today. They are used in white goods, cars, and actually everyone that has a fridge at home has a heat pump. They are used also in commercial application, residential and industrial application, district heatings, and main buildings. In EHPA, we cover almost all of these applications. We also have different committees that represent all different working groups. We work with different types of members, and we have specific working groups for industrial and commercial heat pump members. In the slide, you can see some of them, and we meet, I would say, once every 2 months to discuss the main topics going on related to industrial heat pumps. So if we go more in detail in the technology itself, for industrial heating, today the sources used for industrial heat pumps can go up to 70 degrees. And the sinks, so the application for industrial heat pumps, they can go up to 200 degrees. Of course, there's research innovation going on. We can go even higher, but at the moment we say the mature technologies go up to 200 degrees. Of course, the smaller the difference of the heat source and the sinks, the easier and also the more efficient and less costly the application is because you need less electricity. So you may wonder where is the difference between an industrial heat pumps and a residential heat pumps. Well, of course, they have different, they reach different temperature. An industrial heat pump can reach higher temperatures. And they also have a higher capacity than residential heat pumps. Also, another big difference is, of course, the dimension, as industrial heat pumps can be as big as a whole house. There's a lot of potential for this type of heat pumps. Here you can see in this graph that 37% of process heating in Europe is below 200 degrees. That corresponds to 722 terawatt per hours of industrial heat demand below 200 degrees. And this is a huge potential because at the moment in Europe, we only have an installed capacity of around 7 terawatt per hours. So this means that you would have a potential of 100 times what is currently installed. But there is not only big potential in applying industrial heat pumps, it is also very good for competitiveness in Europe because the heat pump industry has a very strong European basis. So it gives a lot of economic value and job opportunities in Europe. Here you have on this map the headquarters of large heat pump suppliers in Europe. And you see there's quite a lot. And also is interesting is that with these machines, as I said, they are very big. So they are also produced close to the place where they are used. So there's really no need to produce an industrial heat pump, for example, in Asia, and then transport it to Europe. So it's much more cost efficient to produce it close to the place where you work and you use it. Electrifying also with industrial heat pumps comes with a lot of advantages. So if you use fossil fuel to heat, you use around 1 unit of fossil fuel. you use one unit of fossil fuel to have 1 unit of heat. Instead, if you use a heat pump, you have 1 unit of electricity. You can have 3 or 4 units of heat because you use as a basis your source temperatures, which is already higher. And you need just some electricity to compress it and to make the temperature lift a bit higher. So yes, it's very energy efficient, and it's much better for energy security as well, because we are less reliant on imported fossil fuel from countries such as Russia. So to go from the theory to practice, we have different examples of industrial heat pumps already full operational and deployable today. For example, one of the success stories comes from Friesland Campina, a Dutch dairy company where mechanical and thermal vapor recompression has been used successfully in dairy processing for many years. In their powder factories, waste heat from the evaporation process is upgraded and reused to produce hot water for drying, improving a lot its energy efficiency, while also reducing water consumption. In cheese production, heat pumps complement high regenerative transmission and pasteurization processes by covering the remaining heating and cooling demand. So this case really shows that industrial heat pumps are already a mature technology and effective solution, although careful process integration is needed to match heat supply and demand. Other example of already operational industrial heat pumps, we have them in France with a paper factory, also a chemical plant in the UK. And speaking about the food and beverage sector, we also have a French pasta company in France, a dairy factory in Norway, and many more. You can find all the details and read about these stories on our website under the heat pump stories page. So now that we show there is a huge potential, there is a large manufacturing capacity in Europe, and there are also several deployable examples in Europe. You may wonder why they are not really widespread yet. Well, of course, there are some issues to fix. We isolated 5 main issues that you can see here in this slide. So the first one is, of course, economics. As long as the fossil fuel alternative is cheaper, it's very hard to convince to make the switch to another technologies, because there's a lot of more taxes and levies put on the electricity bill, which makes the cost much higher. So for that, we must ensure that taxes and energy costs actually boost electrification. We also have to make sure that industry that actually decarbonize their processes are also financially supported. Secondly, also, of course, regulation. There's a need to be a long-term stable policy to show that really decarbonization is the way to go for all sector. And this could facilitate decision maker, of course, to make an easier choices in factories. Another thing, we should also require the electrification of industrial process when, for example, there is a new permit or a new license for an industry or for a renovation of an industry. It should be required to electrify wherever is possible. Moving forward on energy system, we often hear that if you want to install an industrial heat pump in your factory, that doesn't give you an immediate upgrade to your grid access. And because you need a good access to the grid and to electricity for industrial heat pump, this should really be a priority. So grid investments are really needed. And there's a lack of knowledge and low awareness of these technologies. There are many engineers or CEO of food factories that are not yet aware of the potential of industrial heat pumps and what they can do, and they can actually be a solution for them. And as a last point, another point that many people don't know is that the source for industrial heat pump can also be found inside the industrial process, and it can be there can be a waste heat recovery. So it should be mandatory wherever you have waste heat that you should come up with a plan on how to reuse, which it makes more energy efficient. To complement what I was talking about before about the economics, here in the slide, you can see the comparison of the current electricity to gas price ratio in European countries from small-scale industry and users. And speaking about opportunities, one of them that I would really like to highlight is the Innovation Fund Action for Industrial Heat Decarbonization, initiated by the European Commission. This is a fundamental instrument to accelerate the deployment of industrial heat pumps with up to 1 billion available for projects. So if you are an end user, an industrial end user, or you work with a company, we really encourage to submit a bid because the stronger the signal that this market is real and ready to scale, and the more likely this auction gets institutionalized as a permanent instrument rather than a one-time pilot. So that is it from my side. If you would like to know more about our initiatives and our event in which we can raise awareness about these technologies, you can follow us on our social media, and you can also check our website. And if you have, of course, any specific question, you can always reach out to me. And thank you for your attention.
Thank you very much, Paola. That's very interesting. I second what you said about engineers and facility managers are underestimating the potential of industrial heat pumps. And speaking of waste heat, this takes us to our next presentation, which I will do myself. So allow me to share my screen. Sorry for taking so long. So let's talk about one of the biggest contributors to waste heat in all industrial sectors, and especially in the dairy sector. This is the agenda for the things we would cover. I will try to cover them as much as the time allows me. So, yeah. So actually, we know that refrigeration is consuming almost 30% of energy use in the agri-food industry. And with meat added to this, this constitutes almost 2/3 of the total energy consumption in this sector. And hence, the discussion about measures for energy efficiency for refrigeration-related processes in the sector becomes crucial. So actually, when we take a closer look, we know that 25 to 50% of the total energy cost goes to main stages, including the refrigeration unit of the bulk tank, the vacuum pump, the milk transfer pump, and the water heater, and when present, pre-coolers. So pre-coolers are actually one add-on I think Julia hinted on in her presentation, and let me pick from there rather than re-explaining, but it's a technology that is used to reduce the energy consumption because it takes 22 watts hour per liter of milk at 35 degrees Celsius to cool down 1 liter of milk. And for every 1 degree Celsius we are able to reduce before reaching the tanks, we are able to save almost 0.5 watts hour and per liter. And this actually accumulates to a significant percentage of the energy consumption. So the second recommendation here is variable speed drives, which is the technology implemented in many of household appliances to reduce energy consumption. And knowing that pumps alone are responsible for from 15 to 20% units, and applying speed on top, actually those are 11 degrees temperature through the break uses pump by 80%. That's a significant.
Hi, I think Mu'taz is having some connection problems. Let's just wait a couple of minutes till he reconnects.
Sorry, everyone. Something went wrong with my connection. Please let me know if you can see my screen or I need to share it again.
We can't
Kavya?
see it yet, Mu'taz. I can't see it yet.
We cannot see the screen, but maybe I can share the screen
Okay.
and change
Yes.
slides for you.
Okay. Actually,
Oh, okay. We can see.
Yeah.
Okay.
I changed it. Okay.
If you need
You
me,
can
just
see
tell
it
me.
now. Thank you. So yeah, thank you so much. So given that refrigeration is one of the most contributors to waste heat in all industrial facilities, we actually have two measures here that we can implement since refrigeration in the dairy sector is reliant on the vapor compression refrigeration cycles. And knowing that the compressors take almost 70 to 80% of the electricity input, and by replacing end-of-life compressors with a scroll compressor, actually that reduces cooling cost by almost 20%. And from a regulatory point of view, under the F-gas regulation, the refrigerant 404A is out for new tanks. So replacement should be planned around A2L or natural refrigerants. So heat recovery, actually, it's a unit that's added to the refrigeration part, and it recovers 20 to 50% of the energy needed to cool the milk as hot water at 40 to 60 degrees. Actually, the same principle as in many of the case studies that we covered today, and in many large facilities, they rely on this technology at farm and small plant scale in order to reduce energy consumption. The next measure here is water heaters without tanks, which is the same technology that's used in instant heaters. And actually, this reduces and cuts or limits the standby losses from tank heaters, which is estimated around 24 to 60% per day for tank heaters. So we remove the tank altogether and we save about 90% in some case studies. And actually, we may use solar or geothermal sources to reduce the remaining part. So accumulation again. Of course, the obvious thing that you don't need an expert to tell you is that keeping the facility maintained and in its best operational case actually reduces energy consumption significantly. And also, it's important to keep periodic leak control as required by F-gas regulation, and as well cleaning heat exchanger surfaces every 3 to 6 months in order to improve heat transfer across these systems. So there are other facility level and system level measures here by shutting equipment off when not needed, keep the cooler closed and out of hot zones, and optimizing milking time, monitoring energy performance indicators, and use energy management systems and predictive control. So the next measure is focused on the transport stage of the value chain, and transport consumes no cooling energy in itself, but poor insulation dissipates the energy already spent. So there are two cases of insulation that are defined under the ATB agreement. That's IN at 0.7, the thermal conductance at 0.7, and heavily insulated, which are called IR at 0.4 watts per square meter Kelvin. So implementing heavily insulated tanks for refrigerated transport actually helps significantly with reducing energy losses. So from a technical point of view, the BETTED project here helps small and medium enterprises to identify areas of improvements, and at the same time provides training to these companies in order to help them identify these areas on themselves, and at the same time improve and act on the low-hanging fruit and areas of improvements that they can implement at limited costs. Which actually, this takes us to the training offer that I hinted on earlier. So as Patricia mentioned, the BETTED project offers tailored trainings to companies that are Europe-based in the dairy sector. And this training is tailored based on the company-owned data that actually Patricia as well walked us through. And actually, this training is provided fully funded, free of charge to participating companies. You can find the expression of interest form in the chat box. Kavya, my colleague, will share in the chat box, and you may as well reach out to me directly to discuss your company's needs, and if we can bring the BETTED project benefits and best practices to your company, so you get to benefit from technical guidance and tailored training in company, either on site or online, that's fully funded by the project, which is great. So the key takeaways here, I think, is that the cold production is 25 to 50% of dairy plants' energy cost. We have shared with you proven measures that exist at every stage, and the BETTED toolbox that you can use, and you can get training not only on using the toolbox, but also on the different measures the toolbox allows you to use and allows you to decide on as part of the project, and that's all fully funded by the project. So thank you very much. Please feel free to reach out to me, and as Julia mentioned, we will be sharing with you a questionnaire after the workshop. And with this, we conclude. I think we don't have much time for the Q&A slot that we planned, but Anna, please feel free to unmute yourself and tell us if there are any questions that we can take in those remaining 2 minutes until the end of the workshop.
Thank you. I see that questions are answered in the Q&A section, and there is even the possibility to exchange between the person who asks and panelists who answer. So I guess that we can wait for any questions, and if there are some, we answer. If not, maybe you have, panelists, some questions, or maybe I have.
Okay, thank you so much, Anna. I think there are 3 things that you can do, that our participants can do before they go. So number 1, completing the expression of interest form that's shared in the chat if they are interested in applying for this free in-company training that's limited to only 20 companies and will be delivered by project partners, and the IAR is delivering this training for 20 companies, 20 selected companies across the dairy value chain in Europe. Also, the second thing is that recording and slides will reach your inbox this week. And finally, if you have colleagues who should have seen this, please feel invited to forward them the recording. And we have set a deadline to receiving expression of interests to mid of August. So please, if you are interested, reach out and we will walk you through the process and answer any questions you may have, and have any discussions one-on-one with the responsible team in your company or entity. So thank you very much.
Montes?
Sure,
I have to.
Go ahead.
Yes, I have to interrupt you because we have two
Sure.
questions, and one is related to training. So maybe you could answer, because this is a
Sure.
question about how long the training takes, and how many
Sure.
days are needed to go through the program. And second question is more general about our IIR expertise, so we can take it in the end, I think, to submit.
Sure. So regarding the training itself, the training runs for 1 day, 8 hours in total. The training material is already developed and available in 7 different languages on the project website that you can access. However, the idea of the on-site or in-company training is that we tailor the training to your needs. So if you are already doing well in terms of heating, we will be focusing more on cooling. We will be, and we will try to identify and highlight areas that you can focus on in your facility. So that's like technical guidance from experts for free and funded by the project. And so that's regarding the training itself and the idea of bringing the training to your company. We prefer to deliver the training to a whole value chain, but all interests are welcome, and we will be handling them one by one. So that's regarding the training. IIR's expertise. IIR is an international intergovernmental authority in the refrigeration and cooling science. IIR was established in 1908 with the intention to be the global authority on refrigeration and cooling. Our mission is to promote and enhance science and build the capacity on refrigeration and cooling, and we are engaged in so many projects that you are welcome to check on our website. And actually, subscribers to IIR's or members of IIR get exclusive access to scientific and industry literature and publications. So that's something also, if you are interested to know more about, please feel free to reach me out, and I will direct you to someone to help you with this.
And
so actually, what are okay?
Mortis,
Go ahead.
can I add one sentence?
Please,
about the question? That IIR has to add that IIR has over 390 experts, and actually we have 2 sections which are related to the IIR is divided. The field of refrigeration is divided into different subfields, and actually 2 of them are related to biology and food technology and storage and transport. So I guess that these 2 sections and experts from these sections could support any activities and any questions which are coming from the dairy sector challenges regarding exactly the refrigeration. But fortunately, you have all of the BETTED project umbrella where there are different topics considered, and the materials are available and ready to be used. That's only from me.
Thank you so much, Anna. That's very, very helpful. Actually, we are 5 minutes beyond our meeting time. So thank you so much, everyone. Special thanks to our co-organizers and presenters. and I wish you a productive day. Thank you very much.
Thank you.
Thank you very much.
Thank you.
Thank you. Bye bye.